Good afternoon, everyone. Welcome back. Just if you're new to the channel and this is your first lesson here, welcome. I'm going to try and go through conic sections today, in particular the primary details of the eccentricity method for the ellipse, parabola, hyperbola, and then the double hyperbola as a method in itself. Okay, so I suppose first things first here as well. You know, we just have to understand the title conic sections, okay? So you got to imagine a cone, okay? In the case of an ellipse, if you cut a cone at an angle of less than 45 degrees, you're going to get an elliptical cut surface, okay? In terms of a parabola, if you cut a cone at an angle of 45 degrees, you're going to get a parabola. In terms of the hyperbola, if you cut a cone at an angle greater than 45 degrees, okay, you'll get a hyperbola, okay? So that's the primary distinction between the three main shapes that we deal with in terms of conic sections. Now, I know you guys tuning in, you probably have, you know, done this stuff a while back, maybe. For some of you, this might be a little bit of a refresher, but certainly what I want to do here is I want to focus in on the method and also how we find tangents, centers of curvature, and so on. All those typical aspects to the short answer questions for the conic section, but also as well to realize that the format we have here for these eccentricity and so on is hugely relevant to the long question as well, because we're often given a cut surface on an object, we're asked to find the true shape of it, find the directrix, and so on and so forth, and all of that is relevant to what we're doing here. So we want to look at, you know, conic section short question as opposed to long question, and actually see like there is a huge crossover in terms of, yeah, the base material is still the same. Okay, now I'm going to move to the ellipse here and I'm going to focus in here and we're going to get going straight away. I'm conscious that time is something that I constantly need to improve on. I do like to talk and ramble a little bit, guys, when I'm explaining things, but it's only because I'm trying to get the point across, all right? So we'll just focus in here and we'll try and move on with things as quickly as we can. So for a start, you can probably see I have my question done out very lightly, what I want to get across in this. But before we do, and I'll reveal all that as we move through the stages. The ellipse eccentricity is given, or the ratio for the ellipse is given as 2:3. All right, you're probably going, well, what's that? Okay, well, we use a specific method here that's going to cover each of the different conic sections. All right, eccentricity method is what we use. Now, that ratio 2:3, that is the ratio for a line that is going to guide the curve that we are going to get. In this case, we're going to get an elliptical curve. So the eccentricity line that we're going to generate is going to have a particular angle, okay? And that will be given as a component of the written question itself. So ratio 2:3. That could also be represented as a decimal of 0.66. or a fraction of 2/3, all right? So don't be afraid if you see it given in a different way, 2:3 or 0.66 or 2/3, that's all the same thing. But what does it mean to us? I always look at each of the methods, especially if it didn't identify whether it was an ellipse or not. If I have the eccentricity only, if I have something in, you know, 2:3 or 0.66 or 2/3, I know that these are all less than 1, all right? And if they're less than 1, all right, it means they have an angle of less than 45 degrees, okay? Now, how do we actually go and draw the angle out for a ratio of 2:3 for this eccentricity method? Well, what we'll do is we'll take our marker here, and all I'm going to do is I'm going to get my set square, all right? This directrix line, this is the defining line for the production of our ellipse, okay? This directrix line could be perceived as the line that everything is referenced off, okay? And it's always perpendicular to the axis line, okay? So a directrix line always perpendicular to the axis line. Now I have pre-marked a point F there. I just came out 25 mil for it. Again, that's something that will be given in a question. If it's not, you work a way around to finding it, okay? Now, what I want to do is I want to find the line of eccentricity for this ellipse. So the ratio is 2:3. What I'm going to do is I'm going to focus on the second number here first in that ratio, which is number 3. And I'm going to mark out 3 units because this is what this means. 2 units to 3 units. Okay? And the second number in your ratio is always the one that gets marked out on the axis line. So I'm going to mark out 3 10s, okay? Like so, on the axis line. And I'm going to draw up 2 10s. All right, so that's my 3 units to my 2 units, okay? And I'll draw that one up with a light pink there, okay? And as you can see, there's my 2 units. So I came out 3 units and up 2 units. I hope that's clear enough for you, okay? What I do then is that point that I've found there, all right, that's a point on the line of eccentricity, and so is the point where the axis line meets the directrix. So I now have a point here, and as a result, I can form the line of eccentricity, which is what I'm going to do right now. And for short, we'll write LOE, okay? Not LOL, all right, just LOE. Could be LOL at the end of this. Now, the next step for me is, how do I go about now finding the vertex points for my ellipse, okay? The vertex points being the turning points at either end of the ellipse, okay? One end of the major axis as opposed to the other, yeah? So we're going to have 2 of those in an ellipse as we normally would, all right? So what way do we actually do it? Well, we're going to take a green marker here. From point F, I'm going to draw a line at 45 degrees, okay? From F back to hit the line of eccentricity. So there's 45 degrees. And where it hits the line of eccentricity, I'm going to drop it back down to hit the axis line. Okay? Where it hits the axis line, that now is my point V. Okay? That's my vertex point, V. Okay? I'm going to do the same the opposite way. Okay? Draw a 45-degree line from F all the way to hit the line of eccentricity here. I can put directional arrows on those guys just so when you're looking back over, you can see. And by the way, guys, I uploaded a lot of new content in relation to all of this stuff I'm doing now. Digital resources on the YouTube channel, in the DCG playlist. Have a look at it after the lesson to kind of reinforce what you've just learned, okay? So I drop the line straight back down on this end, and now I get point V1, okay? So V and V1. So I have both ends of the ellipse, so essentially what I have here is the length for a major axis, all right? Now, we don't want to go using the concentric circles method here. We don't want to use this eccentricity method because it's going to apply to all the different conics that we have, the parabola and the hyperbola as well, okay? The only difference with the ellipse and the parabola and the hyperbola is that the ellipse, okay, will be an enclosed curve, whereas the parabola, it only has one vertex point and it'll separate to infinity, and likewise with the hyperbola, okay? But we'll get to that in a few moments. So what I want to do here now is I want to draw what we famously call the lattice rectum line, okay? Now you're probably thinking, this is not a biology lesson or anything, is it? No, it's not, okay? The lattice rectum line, okay? So I'm going to draw it straight up from F. Now I've a lot of things pre-marked here. You just draw that line straight on up there. Now I'm going to call it lattice rectum. And as I always say in school, if you were starting a heavy metal band, that'd be a great name. All right, lattice rectum. Okay, so I have that line drawn up from F. Now what I want to do is from F, I want to step out distances so I can create what are called ordinate lines, okay? And these ordinate lines are going to contain the points for my ellipse, and it's going to give me the curve, okay? This is a relatively quick process, okay? These points can be spread out at any distance, guys, all right? I will keep them even, okay, for the moment, but they can be stepped out at any distance, all right? I'm just going to step them out in 10 millimeter units, okay? And then I'll number them then as well, okay? And then as I come to the end there, it's a little unequal there, so I'll just kind of split the difference there, okay? Just to show you that it's not really that important. So from F to V1, just divide that area up whatever way you want. Doesn't matter. So when I call that 1, 2, 3, 4, and then 5. And then between F and V, we'll go halfway between that, and we'll call that, let's say, our 0.6. Okay? Right in there. Now, so what I want to do is these points 1, 2, 3, 4, and 5, I want to extend them up to hit the line of eccentricity, like so. So everything in blue now, if you're colorblind, just transferring the points 1, 2, and 3, and 4, and 5 all the way up to the line of eccentricity, like so. Okay, and now I'm going, and I'll put directional arrows on those because I do always find you're looking back at this, maybe you might have a snapshot and you might want to know what direction they were going. So I bring them up to hit the line of eccentricity, and now I'm going to project them across to hit the lattice rectum line. Okay. Now, those lines were drawn, all right? Okay. In this space here, there are ordinate lines, okay? And on those lines are going to be the points that we find for our ellipse that give us a shape. I'm also going to draw up that little 0.6 in there, draw it up to hit the line of eccentricity, okay? But project it back to hit the lattice rectum in the opposite direction to the other ones, okay? So what I'll do is I'll put a little set of arrows there just to show you that the lines traveled over like so. That one traveled up and it traveled in. Okay. Now, next thing for me to do. All right. That was just showing you that bit. I want to actually extend those lines down. Now, I'm going to extend them down a specific distance that they already have pre-marked. You guys, you just run them on down there, okay? Because we're going to do both sides of the ellipse in one go here. It's the quickest way to do it. We could find the top points and mirror them over, but this will be just a little bit quicker. So follow me in on this one, okay? Now, I'm going to get my compass. Now, I'm going to use my least fancy compass here because I have a colored pen attached to it because I want you to be able to see the curves a little more clearly. Point of the compass is always on point F for this part of the exercise, all right? Always on point F. And what we're doing is we're measuring to the points on the lattice rectum line. So, for example, I have 0.6 just here. I have 0.1, okay, 2, 3, 4, and 5 right here, okay? I'm going to, from F, swing those points back to hit the original lines that came up from the axis line. So, for example, this line coming up from 0.1 up from the axis line, I'm now going to swing back to hit that line, okay, from the 0.1 on the lattice rectum line. So I set my compass like so for 0.1, and you'll find that the arcs are very slight in this, all right? But don't let that put you off, just do them, okay? Now, so you see that arc intersects there. Let's say we go back to 0.1 for a second. So I swung 0.1, it hits here. I get my marker. All right, I'm going to mark a dot where it hits. Okay, I'm also going to swing the compass all the way around to the other side now to hit the line 1 down on the bottom end. Now I have a second point on the other side, and F is not leaving the or the compass is not leaving point F. I swing that, hits the line 2, bring it around, hits the line 2 in the plan view. Well, I'm calling it the plan view, just the opposite side of the axis line. It's not actually a plan view. Okay, then up to 0.3, swing it back to hit the line. There we go there. Swing it down the other side. There we go there. Go up to 4 now. Swing 4 back to hit the line coming up from 4. Mark it. Go down to the opposite side. Mark it again. Okay, and all the time you see the compass has not left point F. And 5 then, bring it on. Hits the line for 5 here, and again, swing it on the other side. It's there, and then finally, just on the inside there, where 0.6 hits the lattice rectum line, we're going to swing it back in to hit the line. So this is probably your trickiest one if you're doing it. Whereas I'm doing it at a very small scale, and swing it around to hit the line on the other side. Now I have the 2 points there and there. Okay, lovely. And of course the top point of F and the bottom point of F there, all right, same distance both sides, where F meets the line of eccentricity, okay, that lattice rectum line where it intersects the line of eccentricity, that's also a point on the curve, okay? So we would swing that distance around to the other side as well, below F, and that'll give us the point below F. Okay, so I have all my points there now. All I want to do is I want to join those up. Again, join them lightly with a pencil first. Make sure your pencil is nice and sharp and it's light. I have it already pre-drawn, so I'm just going to follow as best I can what I drew there in preparation for today. All the way around. Again, I'm always looking at the point ahead of me. I was mentioned that yesterday in the structural forms lesson. Okay, and all the way around. Okay, now there's my ellipse there. All right, job done. Okay, Couple of things we want to work on now. We want to work on, say, for example, a tangent from a point outside the curve, a tangent from a point on the curve, and then the center curvature. Now, it's a lot to fit in there, but we'll see will it fit. Okay. So first things first, I have a focal point here. I just want to relocate that focal point on the other side. So I have my 2 focal points like I normally would. So I take the distance from V to F, from the vertex to point F, and that's 10 millimeters. So I'm going to step out 10 millimeters from the other end and mark out my point F. There we go. We'll call that F1. So now I have V and F and V1 and F1. Okay. So we'll start with the point outside the curve. Okay. Let's draw a tangent. Right. Let's say we have a point P, and I'm picking a random point P here. Okay. Of course, random tells you there's lines already lightly drawn in there. Okay. What I'm asked here is from point P, draw tangents to the ellipse in both directions, right? One going this way, one going that way. Now, if you've ever seen Only Fools and Horses, all right, very old comedy. There's a character called Delboy in that, and if you were a Delboy character, all you do is you draw the line from P, line it up with the edge of the ellipse, and draw it on. Well, I'm afraid, lads, that won't cut it. Okay, what we're going to have to do here, all right, is we're going to have to show how we find the points of contact between the tangent and the actual the curve. Okay, so I'm going to just use a different color now to say. I'm going to use the red marker. So I'll just load this up into the Canon here, lads, and we'll get going on that. Now, lovely. So what we do here, in this situation, we put our compass on point P, the point of the compass, and we stretch it out to the closest focal point, which is point F. All right. What I'm going to do there is I'm going to swing an arc like so. Okay. You can see that arc. It intersects the directrix line here. We'll call that point A. And here we'll call that point B. Now, what we do is we join points A and B back to the furthest focal point. You'll see that'll be point F1. So I join A back to F1. And I join B back to F1. Like so. Okay? Now, I'll just show you the indication arrows there, that they traveled in that direction. Okay? Now, what do we have here? Where those lines from A to F1 and B to F1 cross the ellipse curve, they're our tangent points. Okay? So from there then, we can simply mark the points. Okay? Here's one here. I know there's a lot of clutter there. We'll call that our point A now in that position. And we'll call this our point B here now in this position. Okay. All we have to do is join P to B. That'll give us the tangent on this side. And you will notice how accurately they work out. All right. Tangent. Okay. And then P to A. Like so. And that'll be tangent 2. Well, it doesn't matter what you call them, lads. There's the tangents from the point P. Okay? So very simple. Get your point P, measure the F, swing an arc where it intersects the directrix, draw the 2 points back to the far F point, which is there, where they cross, those lines cross the curve. They're your tangent points, and you just draw out and connect. Okay? Now, you can see there's an awful lot of lines on that there at the moment. We could have a look at, say, for example, what if we had a point on the curve? If we had a point on the curve, let's say we had a point down down here, we'll call it point X. Okay, let's say we have point X here. Okay, right there, and we're asked, right, point X, let's find the tangent at that point. What do we do? Okay, couple of ways to do this. One, you could look at it and go, right, look, remember back to junior cert, you could take F1 and F2 here. or F and F1 and join them to X, bisect the angle, get the normal, and then get the tangent. Now, in that, there is going to be 3 lines, 3 arcs, and a bit of measuring, and that'll take about 1.5 minutes. The quick way to do this one, all right, in the world of graphics, if you want to call it, the eccentricity method, we can actually use our new setup here to support what we want to get. So I'm going to join a line, and I'll do this in a light color, from F to X, okay, or X to F. See this? Like so, okay? Now, what I can do then is I can get my protractor, and from point F, I can mark, and I get my protractor, guys, and I'm putting it on the line XF at the point F. Like so, okay? And I'm going to mark 90 degrees. Right there. Now, I'm going to join that 90-degree line back to point F. Like so, okay? That makes a right angle in there, doesn't it? Okay, for this particular part. X to F, right angle out. And what we're interested in is where that line crosses the directrix. Okay, I'll put a little arrow in at it. Okay. And if I actually line that point up with my point X, I will get the tangent. And that saves me joining up, bisecting angles, all of that. In just 3 lines, I have the tangent. Okay. So what I'll do there is I'll draw that tangent in a different color. And we will then move on. Like so. Okay. We'll call that tangent 3. So that was from a point that was on the curve. Now, if you look at this, if I was given a point on the directrix and I was asked to find the tangent, well, what would I do? Well, I draw the point back into F, do a right angle back out to hit the curve, and then draw the tangent. So in the reverse method, we're actually able to do something different, all right, but just using the same method. So that's a nice, simple way of actually going about that whole process. Now, I know there's a lot of lines there, all right. Okay, we went through a lot there. There's probably one more thing I'd like to add into that, all right, and that'd be the center of curvature. Now, with the center of curvature, let's say we take a point P on the curve anywhere. Okay, let's say I take this point P here. Okay, I'm going to join F and P, all right, F1 to P and F to P, okay. Now, this creates an angle for me. What I'm looking for here is I'm looking for the normal, okay? And if you remember back to when you were finding a tangent to a point on the curve at, say, a junior cert level with a normal ellipse, you'd find that triangle and you'd bisect the angle up here at point P. So I'm just getting any distance on my compass now, and I'm going to bisect the angle on the line there, like so. So that will give me 2 points here, one on the line FP and one on the line F1P, okay? Again, just reset your compass, keep the same distance, and all we're going to do is find the point where they cross over, and it's right here. Okay, now that's my angle bisected, and that is actually my normal line. Okay, now we draw that normal just onto where it hits the axis line. Now what we want to do is we want to find the center of curvature for the ellipse from here. So here's this line here now, okay? What I'm going to do off that, all right, is I'm going to draw a right angled line, okay? Lining my protractor up on the normal line, okay? That line bisector. Center point of the protractor is on the axis line, and I'm going to mark 90 degrees, okay? So mark your 90 degrees. And what we're going to do is draw a line on out in that direction. Don't worry about the length of it, just draw it on out, okay? Now, so that's the line that's at 90 degrees to the bisector. There it is. What we're going to do is we're going to extend the line on from P and F1 now. Okay, and by the way, you can use F1 or F2. I'm just using F1 here because there's less clutter around here. Now, I have that there. A new point. I've extended the line on to hit the line that's at the right angle, and I've got this point here. Okay, what we want to do is we're going to take the protractor again and line it up on that line now at that point we've just found. So I'm lining it up on the line PF1 at the point I just found, and I'm going to mark 90 degrees again. Okay, And I marked a 90-degree line like so. Nice and light. I'll do it all in a dashed line. All right. Don't worry about the length of it. Okay. Just draw it on out there for the moment. Okay. I think that's probably long enough there. Okay. And what we're going to do finally to locate the actual center of curvature is we're going to extend on that original bisector line that we just had there. Okay. And I'll extend it on with a dotted line. And where it intersects the line, we'll call that our point C. That's our center of curvature. Okay. Now, you look at that now. All right. It looks like a mess. All right. But play that back. Go through the stages. All right. And what I've given you is I've given you every variation that could possibly be asked on the ellipse. Okay. All right. Finding center of curvatures, finding tangents outside the curve, on the directrix, and so on. Okay. What you would have to do in some cases is you would have to manipulate that information to suit a particular scenario. Okay, so that's the ellipse there. I'm going to move it over now to the parabola. All right, now the parabola, the eccentricity method is going to apply here again. Okay, so and that's going to be a ratio of 1:1. So 1:1, or decimal point, that'd be 1.0, or a fraction, that'd be 1/1. So that means that the angle of the eccentricity line is going to be exactly 45 degrees. Now, for argument's sake here, we're just going to mark out the units 1 and 1. So I'm going to take 1 unit, 40 millimeters long. Okay, mark it out on the axis line, and then I'm going to take the other unit straight up from there. Okay, and that'll be 40 millimeters long as well. Oh, bit of a wobble there in the pen. Apologies about that. Now, okay, lovely. So what I'm going to do then is I'm going to form going back to where the axis line hits the directrix, I'm going to form the line of eccentricity, okay? Like so, okay, L-O-E. Now, I'm going to fly through this, all right? I'm going to use exactly the same method as the last time. I'm just going to locate my vertex point now. Point F, draw back at 45 degrees. Drop it down. There's point V right there on the axis line. Okay, now what I want to do, I can't do it back in the opposite direction. They'd never meet because the parabola never meets down around it. So once you have one vertex point, there is no other vertex point. Parabola only has one vertex. All right. So what I'm going to do now is I'm going to step out the distances for my, or actually I'll draw my lattice rectum line first. So from F, draw the lattice rectum line. Again, I have everything pre-marked. Okay, we'll call that the LR. Okay. Mark out your units, whatever you want. Okay. I would mark out maybe just 4 tens here, and that'll do me fine. So I'll mark out 1, 2, 3, and 4. Okay. And then between F and V, I'll go, it's 12 mil, so I'll go 6 mil there, and I'll call that 5. All right. Okay. So draw your lines up now to hit your line of eccentricity. Okay. And then we will draw that on like so over hit the lattice rectum line. No big deals there. All right. Again, I have everything kind of pre-drawn here. I'm going to take the compass now in a second. All right, except this time I'm just going to take the normal compass. All right, and I'm going to go to the point here first to point from compass on point F. Okay, all right. Oh, one thing there, I should have extended those lines down the other side of the line because I'm using the shortcut. All right, so just remember that. Always use that shortcut method. It's going to save you a little bit of time. In terms of mirroring points and so on. Okay, and again, I've done pre-drawn, so I'll show you. Okay, so point F, compass doesn't leave that point now, all right? We want to swing the point 5 back to hit the line for 5, okay? Right there. And I'm going to swing it around to hit the other side as well. Lovely. Okay. Now for point 1. Okay, compass is on F. Swing the point 1 around. We have the point now there, and we have the point on the other side. Lovely. bring it up for point 2, swing it around, point 3, swing it around, and then finally point 4, swing it around, okay, and swing it around. All right, very same as the previous method, and if you want to look at a slower version of that, just go back to the other one, because I don't want to burn up too much time here, all right? So I'll mark off my points as found. Great, lovely. Directly above point F, where the lattice rectum line meets the line of eccentricity, that's a point on the curve. Here, point phi naturally, and all the points here on the bottom half as well. And now what I have here is I have the parabola, all right? So I'm going to draw that like so. Lovely. And then I'll go down on this side here and draw it as well. Okay. Now, that's my parabola drawn. Okay. Very simple. Applied the very same method as we did before. Happy days. Okay. What I want to find a point P. All right. I want to find the tangents from point P, which is outside the curve. First step, we're going to do the very same as what we did earlier. I'm going to take point P. All right. I'm going to measure out to point F with my compass, just like we did in the previous ellipse example. And what I'm going to do here is I'm going to swing my arc to intersect the directrix lines, okay? Now, if you remember from the previous example, right, these were points A and B. And what I did was I joined A and B back to the far focal point, F1. Now, in the case of the parabola, we don't have that point, all right, because the parabola only has one focal point, okay? So what do? Well, we're not joining it to the focal point here. What we're going to do is we're going to take a line out at a right angle off the directrix, all right? So it's a straight line across to hit the curve. And likewise from here, straight out to hit the curve. Okay, so I have now 2 points located on the curve. These are my points of contact. Here's B here, here's A here. Okay, and from point P, I'm just going to join a line now to form my tangent to point A. Like so, call that tangent 1. And then from point P through B for tangent 2. Okay, now the next thing here, let's say we have a point on the curve, okay? Let's say I have a point right here. We'll call it point P, okay? And don't be confused between P, we'll call that P1. Here it is, right here. What do? Well, to find the tangent at this point, what we can do is we can draw a line from P1 back to F. And we draw a line from P straight out, okay? You'll see that line there and the line going there. That technically, this line here, in an ellipse, that line goes back to a focal point. This actually, the reason we use a horizontal line here in the case of parabola is we actually are drawing this line to infinity to meet the next focal point on the parabola, which never happens, okay? So another sad story, sorry about that. All right, now, so point P, we'll put the compass there. We're going to bisect the angle here now. So I'm going to do that very quickly. There's my first arc there. Intersects the line here and here. Reposition your compass. Okay, set a distance. Keep the distance the same for both arcs. Swung from both points. Right about that. Now, and then I draw my bisector line. Okay, now, if I have my bisector line there, okay, I line it up point, I line it up with P like so, and then at a right angle to that line, okay, now let's say for example this point here is, this line here is the normal line, I'll just write that in, normal. To find the tangent to that, which is going to be at a right angle to the normal as it always is, we then just mark 90 degrees, okay? So I'm marking 90 degrees and I'm going to draw it back through point P. I set the protractor up on point P on the normal line and I mark 90 degrees down here. And now I'm going to draw that point back through point P. Okay, I don't have to draw it all the way out from here. Okay, but I will draw it like so. There we go. And that light line you see there, we'll call that tangent 3. Coincidentally enough, if you want to find the center of curvature for the parabola, we would continue on the normal line here to hit the axis line right here. Okay, we do the same as we did for the ellipse now. We're going to get the compass, put it on that point on the normal line. We're going to mark 90 degrees. Okay, and I'll do all these with a dash line now. So I'm going to mark 90 degrees. Okay, now this is probably going to run outside the space I have, but at least it'll give you the idea of what to do. Okay, so I've run that line on. What I'll do is I'll take the line, the original line from P and F. I'm going to run that down now to meet the dash line. All right, so P1F, run that line on down, and what we get here is we get another point. And what we're going to do is a right angle across to meet the normal line extended. So if we have the space, which it might work out, okay, I set up my protractor on that point I've found, like so. All right, I'm going to mark the point, 90 degrees here. And what I'm going to do is I'm going to draw a line there now. And that line's at the right angle to the line P1F. Draw it on through, like so. Okay, and then you're going to extend the normal line on to meet it. I'll need to just bring it a tiny bit further. Okay, that center of curvature point can be really far out sometimes. Okay, and extend on the normal line that we had in the first place. And that gives me point C right here. And that's the center of curvature. Okay, that's a right angle there. That's a right angle there, and so on. Okay, so again, there's pretty much all the variations on anything you can be asked about, you know, for example, the parabola. Now, what I would say to you is in an exam question, when they're giving you a point P maybe on the curve, they might say that point P is located 40 millimeters from the directrix or the point F. So, and you have to locate the point P first, and then you have to find the tangent maybe. So in that case, what you do, if it says from the directrix, you just mark out your 40 millimeters and then draw a horizontal line down to hit the ellipse curve or the parabola curve or whatever it is, and that'll give you the point on the curve. If it's from F, just put the 40 millimeters on your compass and swing an arc to hit the curve either top or bottom, doesn't matter which side, unless it's indicated. So, and you can then locate your point P as well and work any of the methods that we've just gone through there. Okay, now, but moving on to the hyperbola, okay? Now, might be able to run through this one a little more quickly, guys, because we kind of have covered everything we needed to cover there. Now, so as you can see here, I have my directrix. You can see very lightly the detail there. All we're going to do here is we're going to use the eccentricity method. I just want to show you how to apply the ratio, okay? So the ratio is 3:2 for the hyperbola. So that's 3:2 as a ratio. As a decimal, it could be 1.5 because, you know, 2 would be the units out of 1. 1.5, or as a fraction, it could be 3/2. Okay, so we want to find that angle. All right, so 3:2. You take the second number and you mark that on the XY line. So that's 2. So we mark 2 units out and 3 units up. Okay, so very, very quickly there, I will mark out, for example, let's say 2 tens on the actual axis line there. Okay, and then I'll mark up 3 tens as a height. Okay, now I just work it the other way. There we go. Again, I have everything pre-drawn, guys, so use your set square and your t-square like you normally would. I'll just show you the units there. Lovely. Okay, so 2 units out, 3 units up, and what that gives me is an eccentricity line. When I connect it up, it gives me a line with an angle greater than 45 degrees. All right, if your angle was less than 45 degrees, you were doing something wrong. Okay, now, so I have that. Now, again, eccentricity method, guys. I have my focal point here. I want to find my vertex point. So what I want to do is I want to draw a line back at 45 degrees there to hit from F to hit the eccentricity line, and then I want to drop a line straight down from that point to hit the actual axis line, and that'll be point V. Okay. Now, with a hyperbola, same as parabola, it only has one vertex point because it never meets again at the other end. Okay, and it only has one focal point there. So what we're just going to do is we're going to complete out the actual curve using the method we used for the previous example. So from point F now, I'm going to draw my lattice rectum line. Okay, so draw it on out there. No bother there. Just call that LR. Okay. In this case here, between F and V, we have a distance of 15. That's just the way it worked out. So I'm going to mark out a couple of points in between there. So let's say we take that one there, and we'll use that pink line we had there in the first place as well. We might as well reuse that line. Okay. And then here, I'll just go 1, 2, 3. All right. You can see my units are much closer together here, the ones I'm marking out for the ordinate lines. Why? Because that line is much steeper. So if I marked out in tens, I'd have to extend that line on a great distance to actually for them lines to actually hit it. So you want to keep the points a little bit tighter on the hyperbola. That will be my main tip. So draw your ordinate lines. Let's say I just take 2 and 1. I want to save a bit of time. So again, draw them both sides of the line. Okay. Okay. Draw them on out like so. And likewise in here. Okay. And then obviously this line we had for the ratio, we're reusing that there. Again, get your compass, put it on F. All right, let's focus on the points on the inside here first. Okay, I have to project them across to hit the lattice rectum line, of course, before I do that. Like so, like there, and there. And then for these ones up here, like so, and yeah, we'll just focus on them. All right, get your compass, put it on F. We can get down to business now. All right, go to the first one here. Okay, what we want to do there, swing that back to hit. Lovely. And swing it around to hit the other end. Bring it up to the next one. Swing it back. Swing it around. Here, where the lattice rectum line meets the line of eccentricity, swing it around. Go up to the next one. Swing it back to hit the original line. Okay, you're going to notice they're going to be quite tight to the line of eccentricity, and then likewise at the top there, swing it around and swing it around down there. Okay, now, so I have those points. I'm just going to highlight them there now. There, 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 and there. All right, just to note that that's the LOE. Okay, line of eccentricity, and then all I'm going to do is I'm going to join up the points. Okay, now again I have a very light curve drawn in there with a pencil. I'm just going to extend them on like so. Okay, so there you go, and I could just draw it on a little bit further, and likewise around here, just extend them on there. Lovely. Now I have that done. The last thing I want to get onto, all right, I was kind of hoping we'd hit the 50-minute mark about that for this one, would be to actually do the double hyperbola. All right. Now, it's rare that it comes up, all right, but it does come up as a short question, all right, generally, if it does, and it can be included in a long question. So what we want to do there is we want to actually know, we want to know how to do it, okay? So in this situation here, what I have here is I'm given two axis lines. This is normally the way you'd set up with a double hyperbola. You have one's called the conjugate axis and the other is called the transverse axis. Now, don't be afraid of them, all right? Okay, the measurements are given for F1 and F2, all right, and V1 and V2. So you can imagine I'm going to have a curve one side opposing the curve the other side, all right? And now we could go through the process of doing a line of eccentricity thing both sides and double up the work, but this is just kind of an all-in-one method for doing a double hyperbola, okay? What we want to do, all right, and those distances, if you want to practice this yourself between the center point here, we call that point O, all right, point of origin there, all right? Okay, the distance to the vertex points is 20 millimeters in both directions, and to the focal points is 30 millimeters in both directions. All right, it's a small example. You can scale it up, whatever you want to do. First thing I do want to do is I want to draw this particular circle here. So I'm going to put the compass on point O, and I'm going to measure out to my vertex point, either side. Doesn't matter. Okay, and I'm going to draw this circle here. Okay, this circle here is called my auxiliary circle. Okay. Auxiliary circle. Now you're probably thinking auxiliary views. No, don't worry about that. I'll just put it in as ox circ. Okay. Now, I have that. What I want to do is I want to now draw a line either side of that circle. Okay. So I'll use, and that'll be a light construction line. Don't draw it heavy. Okay. And don't worry about the length of it. Okay. So line up with V1. Like so. Draw a line. And then line up with the other vertex point there. Again, draw another line. Don't worry about the length of it. What I want to do now is I want to get my compass and I'm going to swing 2 more arcs. All right. And I'll use a different color for this. Okay. Now, you're probably going, why are we doing all this? This is going to help me find our asymptote lines for this particular setup because they're not given. And remember the asymptote lines from the other day from the structural forms? All right, it's a line that guides the shape of the curve but never meets the curve. They never intersect, okay? So from point 0, I'm going to measure out my focal point 2 here, okay? And what I'm going to do is I'm going to swing an arc now to intersect the line at the side that I had just located off the auxiliary circle. So there and there, okay? Likewise, the other side, 0 out to the other focal point. Again, sure, that's the same distance anyway. So I'm going to swing that around and we're finding those 2 points on the other side. Okay. So there and there. Now we're going to join those points crossways. All right. So for example, if I line up these 2 points diagonally, they should line up with the center. They do. All right. And this is going to be my asymptote in one direction. And if I line up these 2 here, it's going to be my asymptote in the other direction. So again, draw them on like so, okay? So ASYMP for short, asymptote. SYMP. Now, all we have to do, guys, is construct a curve because we want the curve to fit within the boundaries of those asymptote lines, okay? So what I'm going to do, I'm going to get my compass, all right? And this is the method here, all right? Now, you just need to be careful where you're taking a measurement from and where you're stepping it off from. All right. So I have, and I'll use a darker color on this so that you can actually see this, because this is the important part of the hyperbola. And from experience, when I've taught this, this is generally the area that lads get confused with most. Okay. So I'm going to start at V1 here. I'm going to put the point of my compass on V1 and I'm going to stretch it out to point 1 here on the other side. Now you see these points 1, 2, 3, 4, and 5. You can mark them out any distance, guys, all right? I've just put 5 mil between all of them, okay? And they're going to be my ordinate points, okay? Just like I had with the ordinate lines in the previous one. The only thing is here, we're not actually going to draw lines straight up or down from these points. We're going to use them to reference distances for arcs that we're going to swing. So V1 to 1 on my compass. Step back to F1 with that distance, and you're going to swing an arc in this area and in this area. And you're probably going, well, how far down or up? You can swing a full arc if you want. I don't want to swing a full arc because the page is going to look very messy. So I'm swinging an arc here and here. Okay, so that was distance V1 to 1, swung from F1 like so. Now, to locate the point on that arc, because we're going to locate a point on the hyperbola here and here as a result of that, we're going to go to V2 and we're going to measure out to point 1. Okay, and I'm going to put the compass on F2. So V2 to 1 now, put the compass on F2, and what we're going to do is swing an arc. Okay, well, this is there now. Okay, like so and like so. Okay, so now I have a point here on the curve and a point here on the curve where the 2 arcs intersected. Okay. So what I want to do is I want to repeat that. I'm just going to write that one down. Okay. So V1 to 1. I'll put a little arrow there. Okay. From F1. Okay. So V1 to 1 over the opposite side. Okay. And that's swung from F1. And then V2 to 1 from F2. Okay, so that was V2 to 1 and swung from F2. And where they intersect for point 1. Okay, now, so let's say we call that point 1 and that point 1 that we just found. Okay, now I'm going to repeat that. I'm not going to do it for all of them because I'm conscious of time. So now I'm going to go V1 to point 2, go to F1, swing an arc, roughly in that area, swing a second arc roughly below it. You're probably figuring it out now. V2 goes to 2, put it on F2, swing an arc to intersect here, and an arc to intersect here. And now I have point 2. If I do it for V1 to 3, step back to F1, swing an arc, measure from V2 to 3, go to F2, swing an arc, there's 3. Then we might as well go all the way to 5 on this side. And what I'd say to you is once you have the curve on one side, you can mirror it through your conjugate axis over to the other side. You don't have to do it all again. In fact, you'd only have to do a quarter if you wanted to, and you could mirror it through your transverse axis, which is the long axis run this way, and then through your conjugate axis if you wanted to. That would be another way to do it. So I'm measuring from V1 to 4 here now, back to F, swing an arc close to the asymptote line. Okay, then I'm going to take V2 to 4, go to F2, swing an arc, and that'll give me 0.4. And then finally the 0.5. V1 goes to 0.5, step it back to F1, swing your arc close to the asymptote line, swing your arc close to the asymptote line, go to V2, measure the 5, go to F2, swing your arc to intersect, swing your arc to intersect. Okay, and then you have 5. Now, lovely. Okay, if you heard a child screaming there, apologies about that. Not my child, neighbours. All right. So what we're going to do now is connect all those points. All right. We're going to go like so, and it's going to form the hyperbolic curve for us there like so. Now, I would mirror them points across to the other side. Okay. Or if you wanted, you could just, as I said earlier, do a quarter down here and mirror it, and so on. Okay, and then I'm going to join them up. And now what I have is the double hyperbola. Okay, and there are more things you can do onto that, but I think that's sufficient for you today, lads, because we're just 2 minutes past the 50-minute mark. That's whereabouts I kind of wanted to be today. Just to give you a quick recap, all right? Just to have a look, we'll just tip this up and we'll zoom back out and we'll have a little look, okay? So you can see there is a lot of little lines and details in there. But what do? Eccentricity method for all 3 here, here, and here. Double hyperbola method. We looked at tangents to the ellipse from outside the curve, on the curve, centers of curvatures in both cases here. All right, the hyperbola was just a clean method, eccentricity only, and then the double hyperbola method, how to actually take our points from one vertex to the ordinates in the other side, the points where we swing them from, and so on. If you need to look at that again, have a look at it. Okay, again, you can see here with the little diagrams, sketches, the ellipse is always produced when you cut a cone at an angle less than 45 degrees. It's always produced when you cut a cone at an angle of 45 degrees here for a parabola. For hyperbola, it's when you cut the cone at an angle greater than 45 degrees, you get a hyperbola. And then here, you can see the double hyperbola. It's 2 cones, one inverted on top of the other, or mirrored. And then the cutting plane cuts through and we produce 2 curves, okay? And the asymptotes guide the curves. We did that by finding the auxiliary circle first, which is the distance, the center point of the whole lot on the transverse axis. Measure out to your vertex, swing the circle, bring 2 construction lines to either side, take your compass, put it on 0, measure out to your F2, Okay, swing an arc around, or you can swing a full circle if you want, all right, to intersect those lines. They'll give you the points for the asymptotes to be formed in one direction, in the other direction. Then locate your ordinate points 1, 2, 3, 4, and 5 at an equal spacing apart. Doesn't have to be, but you want to keep it neat, do so. I had them 5 mil apart. And then what I did was I took, for example, V1 to 1, I swung it from F1 in I drew it close to the asymptote line on the top side and the bottom side, and then I took V2 to 1, put it on F2, and swung it to intersect that arc, and that gave me point 1 and 1, and I repeated the same methodology then for the other points going forward. Again, I said to you, you could focus on just one quarter, mirror it, mirror it, mirror it, if you wanted to. I did a full half the double hyperbola here, and then mirrored it through here very quickly. Okay, so look, lads, thanks very much. Again, hope you enjoyed the class, and look after yourselves. I'll be online for technical graphics tomorrow. That'll be at 10 o'clock in the morning. I'll be covering solids and contact. For DCG, we're back Thursday at 12 p.m., lads, and we will be covering perspective, I think, is what we'll be looking at. So until then, good afternoon, good evening, and good night.